Greetings, Panthers. It's Dr. Augustine. How are you doing today? I hope you're having a great day. And today we're going to take up the topic of the solubility product constant. In fact, we're going to spend a little more detail on solubility than we've spent in the past. Now, actually, this is a topic that's come up several times. Way back in chapter 4, you were given the solubility rules for ionic compounds in water. You had this big table where you had to memorize a bunch of junk about which things were soluble and which things weren't, which ions were soluble, which things weren't. And if you happen to be in my class, I gave you a simpler version of this. Had a little table that looked like this. Here were the common anions: nitrate, chloride, sulfate, hydroxide, carbonate, phosphate, and then group 1 cations plus ammonia. And the way you read this table is if it's white, it's always soluble. If it's gold, it's never soluble, it forms a precipitate, and if it's green, it's slightly soluble, somewhat soluble. And way back in chapter 4, I actually have a video on this, on precipitation reactions. So if you want to refresh your memory on the precipitation reactions and trying to figure out whether something's going to form precipitate or not, we use this solubility table to predict products, or if it's one of the ones that's not on here, like a sulfide, we could use this more detailed solubility rules. But we could predict whether products were going to form, whether a precipitation reaction was actually going to occur. But as with much of General Chemistry 1, in fact, even General Chemistry 2, chemistry professors lie to you all the time. We always sort of tell you sort of the truth, but maybe the truth you're not quite ready for.
You want answers? I think I'm entitled. You want answers? I want the truth. You can't handle the truth.
Okay, so of course it turns out life is more complicated in the real world than just this simple solubility table. This is a nice set of rules. Helps you figure out or estimate whether a precipitation reaction is going to occur, but it doesn't really get to the heart of the matter. And let's use this as an example. So here's a picture. This is actually from chapter 13, where once again we're talking about solubility, and this is supposed to represent sodium chloride and water. And the point of this figure was that the water molecules slowly dissolve this crystal of salt, and the sodium ions get surrounded by water molecules with the negative side of the molecule pointing towards the sodium ions, and the chloride ions that get surrounded by water molecules also, with the positive side, the hydrogen side of the molecules surrounding the water molecules, and they gradually dissolve, pull off these ions. Okay, so you could think of something like this: NaCl, solid, dissolving to form Na plus aqueous plus Cl minus aqueous. Okay, so that's the dissolution process, but does this just keep happening forever? I mean, if you keep adding more and more and more sodium chloride, does it keep dissolving? Does a solid keep forming sodium ions and chloride ions? And the answer is no. Eventually you hit a point where you cannot dissolve anymore. That is called the solubility limit. And we also introduced the idea of equilibrium back in this chapter, that some ions are dissolving, breaking away, and some are recrystallizing. And when the rates of those things equal one another, then we have reached equilibrium. So in fact, you really could write this equation: NaCl solid in equilibrium with Na plus AQ plus Cl minus AQ. But what do we know about the reaction solubility? And we know that this lies heavily to this side of the equation. That's what this whole table was telling us, that chlorides are always soluble and that sodium ions are always soluble. So what that really means is, by Le Chatelier's principle, we expect this reaction to lie heavily to this side, to the product side of the equation, which tells us K should be very large. Okay, so if we were to write an equilibrium expression for this, we would expect that K would be a very big number, heavily favoring this side, the product side of the reaction. So what all this table is telling us is, if we have a clear square, what that's telling us is we have a very, very favorable reaction and K is a big number. And if we have a golden color square, that's telling us that the reaction is not favorable and the reaction actually lies on the reactant side of the equation. So for example, suppose we take something like a chloride that we know does not dissolve, like silver chloride. So we could write something like this: AgCl solid in equilibrium with Ag plus ions, aqueous, plus Cl minus, aqueous. And we know, or we postulate, that it must be heavily on this side of the reaction. Not very many products are formed because it's telling us, this table is telling us it is insoluble. Same thing up here, chloride ions are insoluble. What that means is K is a very small number. Does that mean that not a single silver ion forms if you put silver chloride in solution, or not a single chloride ion forms? No, what it means is that the K is very unfavorable for the product side to be formed, and it's very favorable to stay as a solid, whereas sodium chloride, the opposite's true. We know it dissolves, so it's going to be heavily favor the dissolution process, which means K is a very large number. So really, this figure that we looked at back in chapter 4, which is a simplified version of this table, all this is telling us is whether the K is large or not. If it's a white color square, it's a very large, favorable process. If it's a golden color, it tells us the K is very small and not favorable. And if it's green, it's somewhere in between. All right, so taking a look at this expression, we can write an equilibrium arrow indicating that either the forward or the reverse reaction can take place, and we can write a K expression the exact same way we've done with all the equilibrium problems. So we would write this silver ion concentration times chloride ion concentration, and we would not include this because this is a solid, right? We never include those in a equilibrium expression. So we get some K expression like this. This has a special name. We call this the solubility product constant. So we write this KSP. And in chapter 17, we have a table of KSP. So KSP for silver chloride turns out to be 1.77 times 10 to the minus 10. And as suspected, because this is such a small number, 10 to the minus 10, if we look at this reaction, we would say 10 to the minus 10, that's going to heavily favor the reactant side of the equation, not the product side of the equation. So KSP is merely telling us what this table was hinting at. This table is hinting at clear ones have a large value for K, golden color ones have a very small value for K. So silver chloride, we said, was insoluble back in chapter 4. That's why, 10 to the minus 10. And if you look at this table, we've got some really small numbers, 10 to the minus 29, and even copper sulfide is 10 to the minus 36, so ridiculously small numbers, which means heavily favoring the reactant side of the equation. Okay, so once we have this piece of information, once we have these numbers, we can then take a look at some problems and calculate things like concentrations at equilibrium, as well as we can actually calculate these KSP values once we know the concentrations when we've allowed a reaction to occur. So that's what our next step is going to be, is to take a look at a couple example problems. So we're going to take a look at two sample problems in this video. The first one is as follows. Solid silver chromate, AgCrO4, is added to pure water at 25 degrees C. Some solid remains undissolved at the bottom of the flask. I didn't mention this, but in order to actually use a KSP, you have to have all phases present. So in other words, you have to have some of the solid in there as well as the ions that are dissolved. Otherwise, you would not necessarily be at equilibrium. You could still be below the solubility limit. You could still be driving more stuff to the product side. So in order to actually use KSP, you have to have some remaining. So this says some solid remains undissolved at the bottom of the flask. The mixture stirred for several days to ensure that equilibrium is achieved. Analysis of the equilibrium solution shows that silver ion concentration is 1.3 times 10 to the minus 4 molar. Calculate KSP for this compound. So look at the type of problem. The type of problem is we know the concentration of one of these ions. You could do that with spectroscopy. You could do that with electrochemistry. There's different ways you can measure concentrations, as you know, maybe a titration. But somehow we figured out what the concentration of one of these ions is. So just like any problem in chemistry, a good place to start is to write down a chemical reaction, especially if you know there's one relevant. So Ag2CrO4, this is a solid. It's going to be in equilibrium. It's going to form silver ions. It's going to actually form two silver ions, Ag plus 1 CrO4 2 minus ion. All right, so there's a good place to write the equation. And then the next thing to do in this case would be to write what KSP is. So KSP, we're going to use the same rules we've been using for every other type of equilibrium reaction. So it's going to be Ag plus squared. Remember, the square has to do with this coefficient out front. So we raise whatever the concentration is to the coefficient of whatever is in the chemical reaction, times the chromate ion concentration, CrO4 2 minus. And that's our KSP expression for this particular reaction. So you notice if we want to calculate, it's asking to calculate KSP for this compound. If we want to calculate it, we need the silver ion concentration, which is given to us in the problem, but we also need the chromate ion concentration, which is not given to us in the problem. So we are going to need to figure out what this concentration is, and we can do that from stoichiometry. We know that for every 2 moles of silver ions that get produced, 1 mole of chromate ion gets produced. So we can use a stoichiometry type expression to figure out what this chromate ion concentration is. So let's set up the problem then. The concentration of chromate ion, CrO4 2 minus, is going to be equal to the concentration of silver ions, which is 1.3 times 10 to the minus 4 molar, or maybe we should say moles Ag plus per every 1 liter of solution, times 1 mole CrO4 2 minus for every 2 moles Ag plus. And if we do that calculation, we find out that 6.5 times 10 to the minus 5 moles per liter would be the concentration of the chromate ions. Good practice is to cancel out the units that are being canceled out. So we still have moles chromate for every liter of solution, so that should give me molarity. So therefore KSP then is simply plugging in the values that we've found or that we were given. So 1.3 times 10 to the minus 4 times 6.5 times 10 to the minus 5. And you may have noticed I forgot to square this. This needs to be squared, the silver ion concentration. And that KSP is equal to 1.1 times 10 to the minus 12. And there are no units on these KSPs. So that's the KSP value, very small number. Now, if you look up in this table, you can say, well, there's an extra sig fig, but it basically agrees with the number that's up in the table. Okay? So that's one way, one type of problem for calculating KSP. You're given some concentration, you know the balanced equation, and once you have one of those concentrations, you can figure out what the other species must be, and you can calculate what KSP is going to be. Let's take a look at a second type of problem. Calculate the concentration of chloride ions in a solution of lead chloride, given that KSP equals 1.7 times 10 to the minus 5, and the concentration of lead is measured to be 2 times 10 to the minus 4. All right, so this one we want to find just the chloride ions, and we're given KSP, and we're also given the concentration of lead. So this might be a good time to stop your video and see if you can figure out how to do this problem without me walking through it, and I'll be back in a second to show us how to solve it. All right, so this problem, we have a little more information than we had on the last problem. We're going to start, as we pretty much always should, with a balanced equation, PbCl2 solid in equilibrium with Pb2 plus aqueous plus 2Cl minus aqueous. And we're going to write the KSP expression for this. KSP is going to equal to Pb2 plus concentration times Cl minus squared. And if we look back at this problem, we notice that we have the KSP, we also have the lead ion concentration, and we need the chloride ion concentration, so we're going to solve for chloride ion concentration. All right, so let's say Cl minus squared is equal to KSP divided by the lead ion concentration. And we need to take the square root of both sides to get rid of that square. So the concentration of chloride ions is going to equal to the square root of KSP divided by the lead ion concentration. That's going to equal to the square root of 1.7 times 10 to the minus 5 divided by 2.0 times 10 to the minus 4. So the chloride ion concentration is going to equal to the square root of 0.085, or in other words, 0.29 molar is the concentration of the chloride ions in this problem. Now let's just shift gears a little bit and let's talk about how can we predict whether a precipitate is going to form. we can predict or calculate when a precipitation reaction will actually form using the reaction coefficient that was introduced a couple of chapters ago. So let's start with our silver chloride reaction again, AgCl. I've drawn these arrows equally, but that's probably not really correct necessarily. So that forms Ag ions plus chloride ions. And in case you've forgotten what this reaction coefficient is, it's the exact same thing as the K expression, concentration of Ag plus times the concentration of Cl minus. We use this under any conditions. Remember, the equilibrium expression is only used when you're at equilibrium. But if you have some random condition where you've just run some experiments and measured some concentrations, you can plug it into Q and see what happens. And you get a curve that looks sort of like this. This silver concentration of silver ion increasing, concentration of chloride ion increasing. And you get three different scenarios. You get a scenario where Q is greater than the KSP value. You get a scenario where Q is equal to the KSP value, or you get a scenario where Q is less than the KSP value. And you can actually use Le Chatelier's principle to help you understand what's happening here. So if Q is greater than KSP, in other words, this region of the curve, what that means is you have more of this stuff than KSP would predict. So in other words, you have more products, because remember, Q is equal to the products. So if you have too much products, what's Le Chatelier's principle going to predict? Le Chatelier's principle is going to predict your reaction is going to shift back to the left. So that tells you your reaction should be precipitating. Okay, so if you have too much on the product side, it's going to shift to the left side, and you should go back to the reactant side, which is actually the solid. So Q greater than KSP results in precipitation. Likewise, if Q is less than KSP, that means we don't have enough of the ions formed, so that means it's actually going to dissolve. So if we put a solid chunk of material into our solution and Q is less than KSP, then it will continue dissolving. So what's happening is it's going to continue driving towards this red line in both cases. And the red line is when Q is equal to KSP and you're actually at the solubility limit. So the red is actually the solubility limit. And you cannot add any additional stuff into the solution or it will precipitate. If you're less than that, you can continue adding until you get to the solubility limit. All right, so three different cases. Q less than KSP, your solid will continue to dissolve. Q equal to KSP, and you're at the solubility limit, you're at equilibrium. Q greater than KSP, and your system is going to precipitate. So a real dramatic example of this is something like this is sodium acetate, and this is called a supersaturated solution. I don't know if you've ever made rock candy before, but it's basically the same idea. You increase the temperature, you get it to a hot state, and then you take a seed crystal and you drop it in, and the seed crystal immediately starts to form crystals. All right, and in this case, it's sodium acetate crystals form. If you Google or if you go on YouTube, sodium acetate precipitation reaction, there's a whole bunch of these videos that you can see this happening in real time. It's beautiful. Looks like frozen occurring. But what's happening is Q is greater than KSP. You've actually dissolved more in this solution than it can hold, and all you need to do is drop one seed crystal in, and it will start proceeding towards this Q equals KSP condition. All right, in the next video, we are going to talk about the difference between solubility and solubility product. They're similar, they're related to each other, but there's a subtle difference and an important difference, and we'll talk about that in our next video.